A single point of light can outshine a galaxy of billions of stars. This is the staggering truth behind the universe's most extreme and rare cosmic phenomena. By the end of this journey, you will understand how these events rewrite the rules of physics and reveal the fate of the cosmos. We will explore the violent collisions that forge gold and the mysterious flashes that vanish in days. What force could possibly shred a star into a stream of gas? How can a single explosion be seen from the edge of the observable universe? Each event is a natural experiment in ultimate destruction and creation. What do you believe is the most powerful force in the universe? The fate of a star caught by a supermassive black hole is both violent and illuminating. It is not a quiet disappearance. Instead, the black hole's immense gravity creates a difference in pull so extreme that the side of the star nearest the black hole feels a force vastly stronger than the far side. This tidal force stretches the star horizontally while compressing it vertically, a process astronomers vividly term spaghettification. The star is literally pulled apart into a long, thin ribbon of superheated gas. This stream then spirals into a glowing disk of debris around the black hole, where friction heats the material to temperatures of millions of degrees. For months, this accretion disk shines with the intensity of an entire galaxy, a brilliant flare against the cosmic dark. This entire catastrophe is a tidal disruption event, and it acts as a natural laboratory. By analyzing the light from this stellar autopsy, scientists can measure the mass of the hidden black hole and learn about the types of stars that orbit the galactic center. Instruments like the Zwicky Transient Facility scan the skies for these sudden, brilliant flares, turning tragedy into data. Each event is a fleeting opportunity to study the invisible architects of galactic structure. But if the shredding of a single star can produce such a luminous beacon, what kind of power must be released when two entire stars meet their end in a single, cataclysmic instant? The sheer violence of a tidal disruption event is eclipsed by an even more catastrophic stellar end. Picture an ordinary supernova, the final, brilliant death cry of a massive star. Now amplify that light by a factor of 100. This is the staggering realm of the superluminous supernova, a cosmic detonation so powerful it can outshine the combined light of every star in its host galaxy for months. These are not merely bigger explosions, they are a different class of stellar demise entirely, and their extreme energy defies simple explanation. Where does such an overwhelming power source come from? One compelling theory points to the birth of a magnetar at the heart of the blast. When the star's core collapses, it might not form a quiet neutron star, but one spinning hundreds of times per second and wrapped in a magnetic field trillions of times stronger than Earth's. As this cosmic dynamo slows down, it dumps a colossal amount of rotational energy into the expanding shell of debris, supercharging the explosion's glow like a bellows feeding a fire. Another, even more radical idea is the pair instability supernova. In stars of truly monstrous size, the core becomes so unimaginably hot that light itself begins to spontaneously transform. Particles of matter and antimatter, like electrons and positrons, are created from pure energy. This process robs the core of the internal pressure holding the star up, causing a catastrophic collapse that triggers a runaway thermonuclear explosion. The star is not just destroyed, it is completely obliterated, leaving behind no remnant, not even a black hole. The light from such an event is a pure, unfiltered signature of total stellar annihilation. Because they are so phenomenally bright, superluminous supernovae act as brilliant beacons across cosmic time. Astronomers use them to illuminate the composition of the early universe, probing an era when the first galaxies were still assembling. Each detection is a clue in the puzzle of how the most massive stars live and die. Yet, even as we begin to understand these stellar powerhouses, they point us toward events of an entirely different, almost incomprehensible magnitude. What cosmic catastrophe could possibly dwarf the complete annihilation of a star? Even the complete annihilation of a star is merely a prelude. The universe reserves its most violent crescendo for the birth of a black hole. In a fraction of a second, a gamma-ray burst can release more energy than our Sun will emit across its entire 10 billion-year lifetime. It is, without hyperbole, the single most powerful explosion possible in the cosmos since the Big Bang itself. But that initial, unimaginable flash of pure gamma radiation is blindingly brief, often lasting less than a minute. For astronomers, the true revelation comes not in the initial detonation, but in its echo. As the ultra-relativistic jet, a beam of particles moving at over 99.9% the speed of light, plows into the thin gas of interstellar space, it creates a colossal shockwave. This collision is the source of the Afterglow, a brilliant, multi-wavelength beacon that can outshine its entire host galaxy for weeks. We see it not just in gamma rays, but as a fading ember across the X-ray, optical, and radio spectrum. This lingering light is a cosmic forensic tool. By meticulously tracking how the afterglow dims and shifts color over time, scientists can reverse engineer the catastrophe. They can calculate the staggering total energy of the blast, map the precise geometry of the jet, and even determine the density of the material the star was embedded within long before it died. These observations have solved a major cosmic mystery, revealing two distinct origins for these titanic blasts. The long bursts, lasting more than 2 seconds, are now linked to the collapse of the most massive stars, a supernova on steroids. The short bursts, mere flashes, are the signature of two neutron stars finally spiraling together in a final, space-time rippling embrace, an event that also forges heavy elements like gold and platinum. Each fading afterglow is a narrative written in light, a detailed chronicle of extreme physics and transformative violence. It tells us not just how things end, but what is left behind. And sometimes what is left behind is not a silent remnant, but an object so perfectly tuned and precise, it acts as a lighthouse for the entire cosmos. The fading ember of a gamma-ray burst afterglow reveals a narrative of ultimate destruction, but some cosmic engines do not fade. They burn for millions of years with a ferocity that defines entire epochs. Deep within the core of certain ancient galaxies, a supermassive black hole is engaged in a perpetual feast. Swirling vortices of gas, dust, and entire stars form a searingly hot accretion disk around this gravitational abyss, and the energy released as this material spirals inward is so immense it outshines every star in its galaxy combined. This is a quasar, the universe's most persistent and brilliant lighthouse. Yet even these steady beacons are prone to violent indigestion. Occasionally, a quasar will experience a sudden, dramatic outburst, a flare in brightness so extreme it can become thousands of times more luminous than our entire Milky Way galaxy. What could possibly cause such a stable titan to erupt? The trigger might be a massive instability within the accretion disk itself. A sudden avalanche of superheated material plunging toward the event horizon. Or it could be the sudden, catastrophic arrival of an enormous gas cloud, a celestial banquet delivered all at once. Sometimes, the flare is the brilliant signature of a tidal disruption event happening right at the doorstep of the monster, a single star being shredded and consumed in a spectacular final act. The consequences of such an outburst ripple across the galactic neighborhood. The flood of intense X-ray and ultraviolet radiation from the flare can blast through the host galaxy, heating and dispersing the cold gas clouds that are the nurseries for new stars. In essence, a black hole's feeding frenzy can sterilize its own galaxy, halting the birth of new suns and shaping its evolution for eons. By studying the flickering light of these distant quasars, astronomers are reading a history of chaotic feasts. Each fluctuation in brightness is a clue, a record of what fell into the void and when, helping us understand how these invisible giants grow and how they command the destiny of the galaxies they anchor. But if a quasar's outburst is a sudden, brilliant spike, what does it mean when a cosmic light simply turns on and stays that way, revealing an object that was hidden in plain sight for decades? The brilliant, steady light of a quasar speaks of a perpetual feast, but some of the cosmos's most transformative events are over in a flash. On August 17, 2017, gravitational wave observatories felt a distinctive tremor in spacetime. It was the final, spiraling dance of two neutron stars, the ultra-dense cores of dead suns, locked in a fatal embrace for over 100 million years. In the last fraction of a second, they collided. This event, known as GW170817, did more than send ripples through the fabric of reality. It ignited a cosmic forge of unprecedented power. The collision created conditions of unimaginable density and heat, a cauldron where subatomic particles were slammed together with such ferocity that they built entirely new atoms. This is the rapid neutron capture process, where atomic nuclei are bombarded by a flood of free neutrons, growing heavier in a heartbeat. In that single, cataclysmic instant, the collision forged a treasure trove of heavy elements, including gold, platinum, and uranium. The radioactive decay of these freshly minted, unstable elements then powered a short-lived but intensely brilliant flare of light, a kilonova. While not as overwhelmingly bright as a supernova, a kilonova's concentrated energy in infrared and optical wavelengths can, for about a week, rival the total light output of its entire host galaxy. This event was a landmark because for the first time we saw it with more than just our eyes. We felt the gravitational waves and saw the light, a perfect marriage of messengers that confirmed a long-held theory. The glittering ring on your finger, the platinum in a laboratory catalyst, the uranium that powers some forms of energy generation, all were born in such violent stellar collisions. A kilonova is the universe's ultimate alchemist, transforming pure destruction into the very elements that make planets and life possible. It reveals that we are literally made of stardust, but of a very specific kind, forged in the most extreme crucibles imaginable. Yet, if a collision can create such brilliance, what happens when a single object spinning at the edge of stability becomes a metronome for the cosmos itself? A kilonova's forge creates elements over days, but some cosmic events are over in a flash. In recent years, automated sky surveys have captured something entirely new, a phenomenon that defies all established categories. A pinpoint of light, blazing an intense electric blue, appears where nothing was before. It climbs to a staggering peak, outshining every star in its host galaxy combined, and then, within mere days, it vanishes. Astronomers call these events luminous fast blue optical transients, or LFBOTS for short. Their entire life cycle is a frantic sprint, over in the time it takes a typical supernova to just begin its rise to prominence. This incredible speed is the heart of the mystery. What stellar catastrophe can possibly unfold so fast, yet shine with such ferocious intensity? The leading theory points to a star's core collapse, but with a dramatic twist. Imagine a massive star that has, through stellar winds or a companion's influence, been stripped completely of its outer hydrogen envelope. When the core of this bare, helium-rich star finally gives way, the resulting explosion has no thick outer layers to slow it down. The blast wave erupts into near-empty space, releasing its energy in a sudden, brilliant flash of blue light, potentially forming a black hole or a rapidly spinning magnetar in its wake. Some researchers propose an even more exotic origin, a star wandering too close to an intermediate mass black hole, a class of object that has long eluded definitive discovery. The star's outer layers are violently stripped away in a scaled-down version of a tidal disruption event, creating a sudden, hot flare of accretion light. The extreme brevity of LFBOTS makes them incredibly challenging to study. Catching one requires telescopes that can scan vast swaths of the sky every single night, and then instantly alert other observatories to swing into action before the light fades forever. Each detection is a precious data point in a brand new field of astronomy, time domain astronomy, which focuses on the ever-changing sky. These brilliant blue flashes are not just oddities, they are urgent telegrams from the universe, telling us that there are entire chapters of stellar death we have yet to read. They push our instruments and our theories to the limit, forcing us to consider that some of the cosmos's most spectacular displays are also its most fleeting. And if a star's death can be so brief and brilliant, what does it mean when we see a light that should not exist at all, a beacon shining from an era before stars were even born? The brilliant blue flash of an LFBOT is a frantic, fleeting scream, but at the heart of ancient galaxies, a different kind of violence simmers for eons before erupting. We have seen the steady, overwhelming glow of a quasar, the signature of a supermassive black hole in a state of perpetual feast, yet these cosmic monsters are not placid. Their dining habits are chaotic, prone to sudden, violent outbursts that defy prediction. These are active galactic nucleus flares, moments when the very heart of a galaxy becomes a runaway engine of light. For a brief period, this single point can surge in brightness by a factor of 1,000 or more, utterly drowning out the combined light of every star in its galactic home. What could possibly trigger such a catastrophic surge in a system that is already unimaginably energetic? One leading suspect is a process we see closer to home, but scaled up to a mind-bending degree: magnetic reconnection. The swirling, superheated plasma of the accretion disk is threaded with immensely powerful magnetic fields. Like overstretched rubber bands, these fields can suddenly snap and reconfigure themselves, releasing a tsunami of stored energy in an instant. It is a solar flare, but one born from the maelstrom around a black hole billions of times the mass of our Sun. The energy released can accelerate particles to near light speed and flood space with intense X-rays and gamma rays. Another trigger could be a sudden, catastrophic delivery of fuel. Imagine an enormous gas cloud or perhaps a star cluster wandering too close to the galactic center. The black hole's gravity violently disrupts this material, funneling a vast new supply of matter into the accretion disk all at once. The system, overwhelmed by this sudden banquet, responds with a brilliant flare of indigestion. For astronomers, these unpredictable eruptions are more than just spectacular light shows. They are rare and precious laboratories. The intense radiation from a flare illuminates the structure of the accretion disk and the jets of material shooting from the poles, allowing scientists to map the chaotic flow of matter at the very precipice of the event horizon. By watching how the flare rises and fades across different wavelengths of light, they can test theories of plasma physics and magnetic field behavior under conditions impossible to recreate on Earth. Each flare is a diagnostic pulse, a momentary glimpse into the volatile engine room that powers the most luminous objects in the universe. It reveals that even the most dominant forces in a galaxy are subject to fits of unpredictable fury, a reminder that stability in the cosmos is often just a pause between cataclysms. And if the heart of a galaxy can flicker with such violence, what does it mean when we find a beacon shining with impossible regularity, a pulse so precise it could set a watch for 1,000 years? The universe has a limit for how large a star can grow before it becomes its own undoing. This limit is defined by a phenomenon of pure, self-destructive physics known as a pair instability supernova. It is the fate reserved for the true titans of the cosmos, stars born with masses between 130 and 250 times that of our Sun. Theirs is not a death that leaves a dense remnant, a black hole or a neutron star as a grave marker. Instead, it is a total and complete annihilation, a stellar existence erased in a single, definitive flash. The process begins in the star's final days, as its core burns through its nuclear fuel at a frantic pace. Temperatures soar to billions of degrees, and the core becomes so unimaginably hot that the very nature of light inside it changes. The gamma-ray photons, which provide the outward radiation pressure that holds the star up against its own immense gravity, suddenly find themselves with too much energy. In this extreme environment, these photons of light spontaneously transform into pairs of matter and antimatter, specifically electrons and positrons. This transformation is catastrophic. It robs the core of its supporting pressure almost instantly. Without that outward push, gravity wins in a sudden, violent collapse. The implosion heats the core even further, now packed with helium and oxygen, to a critical point where runaway nuclear fusion ignites. The entire core detonates in a thermonuclear blast of such ferocity that it does not just blow off the star's outer layers, it completely unbinds the star from the inside out. Every bit of stellar material is blasted into space at tremendous speeds, leaving absolutely nothing behind. The light from this total disintegration is staggering. A pair instability supernova can reach a peak brightness that outshines an entire small galaxy, a brilliant temporary beacon signaling the end of a cosmic giant. Because they require such massive, pure stars of primarily hydrogen and helium, these events are thought to have been far more common in the early universe, in the first few 100 million years after the Big Bang. Each one was a cosmic foundry, violently seeding the pristine cosmos with heavy elements like iron, oxygen, and silicon. This enriched material then became the building blocks for the next generation of stars, planets, and ultimately us. So, what does this complete erasure teach us? It defines a fundamental boundary in stellar physics. It shows us there is an upper limit to how much mass a star can hold together before the laws of quantum mechanics and gravity conspire to make it vanish in a blaze of glory. The pair instability supernova is the universe's ultimate reset button for its largest stars, a reminder that some creations are so immense their only possible end is to become pure energy and legacy. And if a single star can be erased so completely, what happens when two stellar corpses, already impossibly dense, are thrown together in a final, space-time shattering collision? The total annihilation of a star in a pair instability supernova is a definitive end, but some stellar corpses are far from dead. They are cosmic pressure cookers waiting to explode. A magnetar is the collapsed core of a massive star, a city-sized ball of neutrons, but it possesses a secret weapon of unimaginable power. Its magnetic field is not merely strong, it is 1,000 trillion times more intense than the field that guides a compass on Earth. This magnetism is so potent it warps the very atoms at the star's surface and creates a rigid, crystalline crust of neutron-rich material, and sometimes that crust cannot contain the stress. The titanic magnetic fields beneath it twist and writhe, building up strain until the crust suddenly cracks. This is a Magnetar giant flare, a starquake of cosmic proportions. In less than a single heartbeat, this event unleashes more energy than our Sun will radiate across 100,000 years. The initial burst of gamma rays is so overwhelmingly concentrated that, for that fleeting instant, this single point outshines every other gamma-ray source in our entire Milky Way galaxy combined. It is as if a lighthouse for one blinding flash became brighter than every other light on the planet. While the main spike of gamma rays lasts only milliseconds, the aftermath tells a longer story. The shattered crust continues to vibrate, ringing like a bell and producing pulsating X-ray afterglows that can be observed for minutes afterward. In some cases, these events are linked to mysterious, milliseconds-long bursts of radio waves detected from other galaxies, suggesting a magnetar's violent snap might be a universal signature. The reach of these flares is almost incomprehensible. In 2004, a magnetar flare from a star about 50,000 light-years away, well outside our galactic neighborhood, still managed to measurably ionize Earth's upper atmosphere. A starquake on a city-sized object halfway across the galaxy briefly altered the very edge of our planet's protective shield. This extreme physics makes magnetars a crucial link in understanding the zoo of high-energy transients in the cosmos. Their sudden, violent releases of magnetic energy offer a model for how other, more distant flashes of radio waves and gamma rays might be powered. They are nature's ultimate electromagnets, demonstrating that even in death, a star can hold onto a force of such concentrated fury that its occasional shudders can be felt across interstellar space. The universe often teaches us through scaled-down models. Within our own Milky Way, miniature versions of those brilliant quasars rage in binary star systems. These are microquasars, and their sudden, violent outbursts reveal the fundamental mechanics of cosmic power on a comprehensible scale. A microquasar consists of a stellar mass black hole or a neutron star locked in a tight gravitational dance with a normal, Sun-like companion star. The compact object's intense gravity steadily strips material from its partner, funneling it into a glowing, superheated accretion disk. For long periods, this system simmers quietly. Then something shifts. The flow of stolen gas becomes a torrent, flooding the disk and triggering a dramatic instability. The system erupts. The microquasar can surge in brightness by a factor of 1,000, becoming the dominant source of X-rays and radio waves in its entire sector of the galaxy. For a brief period, this single binary star system outshines every other object in its local neighborhood, a stellar-scale replica of a quasar's fury. From the vast distance of another galaxy, such an outburst from a mere stellar system could be mistaken for a far more cataclysmic event. Its pinpoint of intense light could briefly rival the diffuse, combined glow of millions of ordinary stars in its host, creating a false signature of a supermassive monster awakening. This is why studying microquasars is so crucial. They are our local laboratories. By observing their flickering X-ray light, the launching of their miniature relativistic jets, and the precise timing of their outburst cycles, astronomers can decipher the physics of accretion in exquisite detail. We can watch in real time how infalling matter behaves under extreme gravity, how magnetic fields twist and launch jets, and how an engine transitions from a quiet hum to a deafening roar. The principles learned here around a black hole just a few times the mass of our Sun are directly scalable to the supermassive behemoths at the hearts of galaxies. How does a small-scale accretion event mirror the behavior of a galactic giant? The laws of physics are universal. A microquasar's outburst is a masterclass in the violent, luminous language of gravity and plasma, spoken in a dialect we can observe up close. It proves that the same cosmic engine, whether powered by a star or a galaxy-killing giant, operates on the same fundamental rules. If a stellar system can mimic a quasar, what does it mean when we find a light that does the opposite, shining with the quiet, steady intensity of a star, but born from a cataclysm of unimaginable scale? The universe's most energetic flashes are not confined to the realm of visible light or gamma rays. Some of its most powerful messages arrive as whispers on the radio. From galaxies billions of light-years away come millisecond-long blasts of radio waves so intense they carry the energy our Sun emits over 80 years. These are fast radio bursts, and for years, each one was a singular mystery, a catastrophic one-time event that left astronomers with only a fading echo and a profound question. Then everything changed. We found repeaters, a specific source in a faint, distant galaxy began flashing again and again, sometimes in frantic, unpredictable clusters. This simple fact ruled out any theory requiring the complete destruction of the source. Whatever was creating these bursts was surviving the event, a cosmic engine that could fire over and over. The prime suspect, once again, is a Magnetar, the neutron star with a magnetic field of almost incomprehensible strength. One compelling idea is that the star's crust, under unimaginable magnetic stress, periodically fractures in a starquake, releasing a focused beam of radio energy along its magnetic poles. Another possibility involves the Magnetar plowing through a dense cloud of debris, perhaps the remnants of the star that formed it, with each interaction creating a shockwave that powers a brilliant radio flash. The sheer intensity of these bursts points to something even stranger than raw power. To appear so bright from such impossible distances, the radio waves cannot be ordinary, chaotic emissions. They must be coherent, like the light from a laser, with trillions of photons marching in lockstep. Some natural process is creating the universe's most powerful radio laser, beaming it across intergalactic space. While a single burst lasts only an instant, a prolific repeater, firing off thousands of bursts over time, can collectively produce a radio signature that stands out against the quiet hum of its entire host galaxy. Each repeating pattern we detect is a vital clue, a fingerprint of the engine's environment and its internal clockwork. The enigma of these repeating radio bursts forces us to refine our models of the most extreme matter in the universe, asking how a city-sized object can store and release such focused energy on command. It suggests that some of the cosmos's most brilliant signals are not announcements of an ending, but the persistent, erratic heartbeat of a surviving powerhouse. And if a single, surviving object can broadcast such focused energy, what does it mean when we find a light that is not a point, but an immense, integrated structure, a glow woven from the death cries of countless stars? But not every brilliant flash signals a star's final act. In the cosmic theater, some of the most spectacular performances are not the closing scene, but a dramatic, violent interlude. These are the Supernova Imposters, eruptions of such staggering scale they can briefly outshine every star in their galaxy, yet the star itself survives. The most famous example is Eta Carinae, a true monster of a star in our own Milky Way. In the 1840s, for reasons still not fully understood, it violently expelled an enormous amount of material in an event called the Great Eruption. For over a decade, it became one of the brightest stars in the southern night sky, a luminosity that, from our vantage point, temporarily rivaled that of a true supernova. Yet when the cosmic dust settled, Eta Carinae was still there, now hidden within the beautiful, expanding homunculus nebula, a cloud of its own shredded outer layers. What could possibly cause a star to undergo such a catastrophic outburst without crossing the line into total destruction? The leading candidates are a class of stars known as luminous blue variables. These are among the most massive, unstable, and radiant stars in existence, constantly teetering on the edge of gravitational collapse. They possess such powerful radiation pressure from their cores that their outer envelopes are barely bound by gravity. In these extreme conditions, the star can become critically unstable, perhaps due to fluctuations in its internal nuclear burning. The radiation pressure overcomes gravity in a massive, violent pulse, ejecting a sun's worth of material into space in a single titanic belch. This is not the core collapse of a supernova, but a surface eruption of unimaginable scale. For astronomers, catching an imposter in the act is both a challenge and a golden opportunity. Because the star survives, we can observe the aftermath directly. We can study the chemical composition of the ejected nebula, which tells us what elements were churning in the star's outer layers. We can monitor how the star's brightness and temperature recover or fail to recover from the trauma. Most importantly, these events are thought to be previews, final rehearsals before the ultimate performance. A star like Eta Carinae is almost certainly destined to end its life in a spectacular supernova or even a hypernova, possibly within the next astronomical instant, which could be any time in the next 100,000 years. Each imposter eruption is a vital clue, a chapter in the life story of the universe's most massive stars, showing us that their journey to a final, definitive explosion is often paved with violent, luminous outbursts. If a star can shine with the light of a supernova and live to tell the tale, what does it mean when we find a light that does the opposite, a beacon that shines with impossible steadiness, born from the most chaotic event imaginable? The erratic heartbeat of a Magnetar is one thing, but to witness the focused fury of an entire galaxy, you must be staring directly down the barrel of a cosmic gun. This is the unique and violent perspective offered by a blazar. At the core of a distant galaxy, a supermassive black hole is not just feeding, it is launching twin jets of matter and energy from its poles, accelerating particles to within a fraction of light speed. When one of those devastatingly powerful beams happens to be aimed almost perfectly at our solar system, we see not the galaxy itself, but the blinding glare of that jet. We call this a blazar, and its light is not a gentle glow but a searing torrent of the highest energy radiation the universe can produce. The intensity of this beam is not steady. It flares and flickers with violent unpredictability. A sudden avalanche of new material into the black hole, or a massive shockwave traveling down the length of the jet, can trigger an outburst of staggering power. During these flares, a blazar can become the single brightest persistent source of gamma rays in the entire sky, outshining the combined high-energy light of every single star in its host galaxy. Instruments like the Fermi Gamma Ray Space Telescope watch these cosmic lighthouses for these sudden, brilliant pulses, monitoring the violent heartbeat of a monster we cannot see directly. This extreme orientation is a gift for science. By staring straight into the jet, we get a clear, head-on view of the most energetic processes in the universe. The rapid fluctuations in brightness tell us about the structure of the jet itself, the size of the region where particles are being accelerated, and the chaotic environment just outside the black hole's event horizon. It is a natural particle accelerator of impossible scale, and its light is the data stream from that experiment. How does a black hole, an object defined by its ability to trap light, create and focus such an incredibly powerful beam of energy? The answer lies in the twisted magnetic fields and superheated plasma of its accretion disk, which can funnel and collimate escaping material into these narrow, relativistic escape routes. Studying a blazar's flare is like watching a lightning storm from directly beneath the cloud, a privileged and terrifying view of nature's raw power. It complements our understanding of all jet-producing phenomena, from microquasars in our own galaxy to the brilliant quasars seen from the side. Each flicker from a blazar is a coded message about the physics at the very edge of possibility, a reminder that the universe's most brilliant lights are often its most dangerous, and that perspective can turn a distant galaxy into a blinding, elemental beacon. A blazar's beam is a focused torrent from a galactic core, but brilliance can also emerge from a far more intimate stellar drama. Even a surface explosion, when placed against the right backdrop, can command the cosmic stage. In the quiet outskirts of a galaxy like our own, a classical nova is a remarkable but localized event. It begins with a binary star system, a pair locked in a gravitational embrace. One star has aged into a white dwarf, an Earth-sized ember of stellar carbon and oxygen, while its companion remains a normal, hydrogen-rich star. Over centuries, the white dwarf's gravity steadily steals this hydrogen, pulling it onto its own incredibly dense surface. This stolen gas accumulates, compressing under the relentless pull of the white dwarf's gravity until the base of the layer reaches a temperature of millions of degrees. Then it ignites. A runaway thermonuclear fusion reaction rips across the white dwarf's surface in a matter of seconds. The star does not die in this event. It merely erupts, violently ejecting the accumulated layer into space in a brilliant shell of expanding gas. For a few days or weeks, this single point can increase in brightness by 50,000 times or more, outshining its entire stellar neighborhood. Yet, against the combined light of a sprawling spiral galaxy, it is usually a notable but not dominant spark. But place that same spark in a different environment, and its story changes completely. Journey to the heart of a galaxy, like the dense core of our own Milky Way, or into the tightly packed globular clusters that orbit it. Here, stars are not isolated points of light. They are a swirling, crowded metropolis. In these stellar cities, the sheer number of binary systems dramatically increases the odds of a nova occurring. And when one does erupt, its brilliant flash is set against a very different background. Instead of the faint, diffuse glow of a galactic disk, the backdrop is itself a concentrated blaze of ancient starlight. In this context, the nova's sudden, piercing point of light can, for its brief lifespan, become the single brightest feature in that crowded sky, a stellar flare that momentarily outshines the integrated glow of the millions of stars packed around it. This environmental amplification makes nova in dense clusters and galactic cores crucial objects of study. By comparing their light curves and chemistry to those in quieter suburbs, astronomers learn how the crowded conditions influence the binary stars themselves, potentially altering their orbits and mass transfer rates. Furthermore, because the peak brightness of a certain type of classical nova is remarkably consistent, they serve as standard candles. Measuring how bright they appear from these dense, distant systems helps astronomers pin down the scale of our galaxy and beyond. So, while a nova may be a surface event on a single star, its perceived brilliance is a conversation between the star and its surroundings. It asks us to consider not just the power of the explosion, but the canvas upon which it is painted. A single match flame is easily lost in a sunlit meadow, but in a dark stone cathedral, it can define the entire space. The nova in a dense cluster teaches us that context is everything, that the universe's drama is often a matter of placement and perspective. And if a surface flash can be magnified by a crowded stellar city, what must it be like when the city itself, an entire galaxy, is the source of the violent, transforming light? A star's surface eruption is a temporary spectacle, but its core is its true engine. What if that engine were not a burning ball of gas, but a city-sized diamond forged in a supernova? This is the bizarre and beautiful premise of a Thorne Żytkow object, a theoretical stellar hybrid that is one of the most exotic ideas in all of astrophysics. Picture a red supergiant star, one of the largest and most bloated stars in the universe, so vast that if placed in our solar system, it would engulf the orbit of Jupiter. Now imagine that at the very heart of this tenuous, distended giant, there is not a typical fusion core, but the ultra-dense remnant of a previous stellar catastrophe, a neutron star. This is not a binary pair, it is a stellar matryoshka doll, a neutron star completely embedded within and powering the envelope of a giant star. How could such a thing form? The most likely path is through a slow, cosmic dance of decay. Two massive stars are born as a binary pair. The more massive one explodes first as a supernova, leaving behind its neutron star core. Over millions of years, as the companion star ages and swells into a red giant, its outer atmosphere expands until it engulfs its neutron star companion. Instead of being ejected, the neutron star spirals inward through the diffuse outer layers, a process of drag and decay, until it comes to rest at the very center, replacing the star's original core. The physics inside such an object is utterly alien. The neutron star, with a surface temperature in the millions of degrees, acts as a potent internal furnace. It bathes the surrounding hydrogen envelope in intense heat, driving unusual nuclear fusion reactions not found in normal stars. The expected signature of this internal strangeness would be visible on the surface. Astronomers predict the atmosphere of a Thorne Żytkow object would be laced with unusually high amounts of certain heavy elements like lithium, rubidium, and molybdenum, elements typically destroyed in ordinary stellar cores. It would also glow with a distinct, slightly peculiar spectrum of light. For decades, this has been a purely theoretical construct, a fascinating thought experiment written in equations. The hunt for a real candidate, however, pushes telescopes and analysis to their absolute limits. It requires sifting through the light of millions of red giants, looking for that one spectrum with a bizarre chemical fingerprint that cannot be explained by any standard model of stellar evolution. A few stars, like HV 2112 in the Small Magellanic Cloud, have shown tantalizing hints, but none have provided definitive proof. The ultimate fate of such an object is as mysterious as its life. If the neutron star core eventually accretes enough mass from its host envelope, it could collapse into a black hole, potentially triggering a supernova explosion of a type we have never witnessed. Or the envelope might be gradually stripped away, revealing the bare neutron star once more. The mere possibility of Thorne Żytkow objects stretches our understanding of what a star can be. They represent a hidden chapter of stellar evolution, a reminder that the universe's menu of celestial objects is far more diverse and inventive than our current catalog suggests. If stars can form with such bizarre internal engines, what other impossible-seeming hybrids might be waiting in the dark, their light carrying the signature of a structure we have not yet dared to imagine? The most brilliant lights in the cosmos come from the annihilation of matter. But what if the universe's most abundant form of matter is also destroying itself in the dark? This is the profound mystery of dark matter annihilation. We cannot see dark matter directly, as it does not emit, absorb, or reflect light. Yet its gravitational pull is undeniable, sculpting galaxies and holding clusters together. Its nature remains the greatest unsolved puzzle in modern cosmology. One compelling theory suggests dark matter particles could be their own antiparticles. If this is true, then when two of these particles collide in the void, they would annihilate each other in a flash of pure energy, transforming into a spray of standard particles we can detect, such as gamma-ray photons. The key is density. In the diffuse halo of a galaxy like our Milky Way, these collisions would be vanishingly rare, producing only a faint whisper. But journey to the places where dark matter is thought to be most densely packed, the very hearts of galaxies, or the ancient star-poor dwarf spheroidals that orbit them. Here, in these gravitational wells, the concentration of dark matter could be so immense that the rate of mutual annihilation might spike. The result would not be a pinpoint flare, but a steady, diffuse glow of high-energy gamma radiation emanating from the entire region. In an extreme theoretical scenario, this pervasive gamma-ray haze could, in principle, rival or even exceed the total output of visible light from all the stars in that system. The galaxy's light would have two sources: the familiar fusion furnaces of its stars and the silent, particle-level destruction of its unseen scaffolding. This is not science fiction, it is a serious hunt. Gamma-ray observatories like the Fermi Space Telescope spend years meticulously mapping the sky, not just looking for brilliant bursts, but for these subtle, persistent excesses of radiation that cannot be explained by known astrophysical processes. They scrutinize the centers of galaxies and the faint dwarf spheroidals, searching for that telltale spectral signature of annihilation. A confirmed detection would be a monumental breakthrough, finally revealing the identity of the universe's hidden mass and opening a direct window into particle physics at energy scales far beyond any terrestrial collider. It asks a deeply philosophical question. Could the light we use to understand the universe ultimately be outshone by the glow of its own invisible foundation? This search reminds us that illumination can come from the most unexpected transformations, and that the universe's greatest secrets may be written not in starlight, but in the silent, high-energy whispers of its own shadow. The silent glow of dark matter annihilation is a whisper from the universe's hidden structure, but its birth pangs were anything but quiet. To understand the origin of the heaviest elements and the most brilliant flashes, we must return to the death of the very first generation of stars. These were not the well-mannered giants we see today, but colossal, pristine behemoths born from only hydrogen and helium. Their fate was the hypernova, a term that captures an entire suite of catastrophic processes. A hypernova is not merely a bigger supernova. It is the violent signature of a star's core collapsing directly into a black hole, an event so transformative it forges the very fabric of new elements and lights the cosmic dark for eons. This specific collapse mechanism is called a collapsar. It begins with a star of immense mass, perhaps 40 times that of our Sun or more, and crucially, one spinning rapidly. As this titan exhausts its nuclear fuel, its iron core catastrophically implodes under its own weight. In a standard supernova, this forms a neutron star, but in a collapsar, the core's mass and angular momentum are too great. It bypasses the neutron star stage entirely, collapsing directly into a newborn black hole. But the story does not end with a silent birth. The infalling material from the outer layers of the star possesses tremendous rotational energy, forming a searingly hot, dense accretion disk around the fledgling black hole. This disk becomes the engine for the most relativistic jets in the universe. Like a cosmic blowtorch, these jets of plasma, moving at over 99.9% the speed of light, drill their way out through the star's outer envelope. Their successful breakout is what we observe as a long-duration gamma-ray burst, that initial, blinding flash of the highest energy radiation. The supernova explosion that accompanies this internal drama is itself of a different class. The energy deposited by the jets and the sheer scale of the collapse create a blast of unprecedented power. The hypernova synthesizes a staggering amount of radioactive nickel-56, perhaps 10 times or more than a typical supernova. As this nickel decays into cobalt and then iron, it releases a flood of light that powers the optical display. The resulting supernova is not just bright, it is enduring, outshining its entire host galaxy for months with a light curve that decays slowly, a lingering testament to the sheer quantity of radioactive fuel created in the blast. This model elegantly ties together three cosmic phenomena into one catastrophic framework: the death of a massive, rotating star, the birth of a black hole with relativistic jets, and a supernova of extraordinary luminosity. It explains how the R process, which forges the heaviest elements like gold and uranium, might be seeded by material ejected from the accretion disk or the jet cocoon. A hypernova is therefore a cosmic crucible and a brilliant beacon, a single event that forges new elements, announces the birth of a black hole, and illuminates the early universe with a light that can be seen across billions of light years. It represents the most extreme pathway of stellar death, where gravity's final victory is so complete it unleashes the very forces that light up the cosmos. The hypernova's brilliance is a testament to the extremes of stellar mass, but the universe hides monsters of a different, elusive class. For decades, black holes have seemed to exist in two distinct families: the stellar mass remnants of dead stars and the supermassive behemoths anchoring galaxies. Between them lies a vast, mysterious gap, populated by what should be the missing link: intermediate mass black holes. These objects, weighing hundreds to thousands of solar masses, are the cosmic middleweights, and their feeding habits could produce some of the most telling flares in the sky. Imagine a star, perhaps similar to our Sun, wandering too close to one of these gravitational traps. The disruption would be both familiar and profoundly different from the events around a supermassive giant. A supermassive black hole's immense event horizon allows it to swallow a star hole relatively quickly, producing a sharp, brilliant spike of light. An intermediate mass black hole, however, is smaller. Its event horizon is tighter, its gravitational grip less overwhelmingly dominant at a distance. This changes the entire rhythm of the catastrophe. The tidal forces would still tear the star apart, but the process might be slower, more drawn out. The stream of stellar debris would take longer to spiral inward, and the resulting flare from the accretion disk could rise and fade over a distinct, measurable timeline that acts as a fingerprint for the black hole's mass. The light itself would carry a unique spectral signature, a mix of temperatures and emissions shaped by the physics of a mid-sized gravity well, but the true spectacle lies in the contrast. Intermediate mass black holes are not thought to dwell in bright galactic cores. They are likely hidden in the dense hearts of ancient globular clusters or wandering through the faint, dwarf galaxies that orbit larger ones. These environments are dim, their total starlight a soft, collective glow. Against this quiet backdrop, the flare from a single disrupted star would be utterly transformative. For weeks or months, this one point of light could outshine the combined output of every other star in its entire host cluster or dwarf galaxy. It would be a brilliant, unmistakable beacon in a sea of relative darkness, a temporary lighthouse announcing the presence of the invisible monster at its core. This makes the hunt for such an event a dual quest of the highest value. Catching the flare would immediately confirm the existence of the black hole itself, solving a long-standing astronomical puzzle. Simultaneously, it would provide a pristine laboratory to study the physics of tidal disruption in a mass regime we have never directly witnessed. The data would reveal not just the black hole's mass, but the composition of the star it destroyed and the detailed mechanics of how matter falls into a mid-sized abyss. Each candidate flare scrutinized by telescopes brings us closer to filling the evolutionary gap between stellar and supermassive black holes. It asks whether these middleweights are the seeds from which galactic giants grow, or if they represent a separate, parallel lineage of cosmic predators. The violent end of a star, therefore, becomes more than just a light show. In the right context against the right dark canvas, it becomes a precise diagnostic tool, a key that can unlock two cosmic mysteries at once. It highlights a stunning diversity in the universe's destructive forces, proving that scale is everything, and that sometimes the most revealing events occur not in the brilliant city centers, but in the quiet, overlooked neighborhoods of the cosmos. Even the middleweight monsters have a limit to how brightly they can shine, a rule written in the balance of radiation and gravity. This is the Eddington limit, the maximum luminosity a star or compact object can achieve when the outward pressure of its own radiation perfectly balances the inward pull of its gravity. Push past this limit, and the radiation should blow the inflowing matter away, shutting off the fuel supply. Yet scattered across nearby galaxies, astronomers find pinpricks of X-ray light that gleefully shatter this rule. These are ultra-luminous X-ray sources, or ULCs, and they burn with the fury of millions of suns, concentrated into a single, searing point. For years, their identity was a profound puzzle. Their incredible brightness suggested they must be powered by accretion onto black holes of an intermediate, elusive mass. But then we caught one in the act of pulsing. A steady, rapid beat emerged from the X-ray glare, a telltale signature of a spinning neutron star's lighthouse beam sweeping across our line of sight. This changed everything. It meant the engine behind this phenomenal brightness was not a black hole of any size, but a city-sized remnant of a dead star, a pulsar. How can such a small object with a surface gravity that should enforce the Eddington limit burn so impossibly bright? The answer lies in the neutron star's secret weapon, a magnetic field of almost unimaginable strength. In a typical accretion scenario, matter falling onto a neutron star forms a disk and spreads evenly over its surface, quickly hitting the luminosity ceiling. But in these pulsating ULXs, the magnetic field is so powerful it acts as a cosmic funnel. It seizes control of the incoming stream of stolen gas from a companion star, channeling it directly onto the neutron star's magnetic poles. This creates two incredibly hot, focused spots where matter impacts the surface at nearly the speed of light. By confining the accretion to these small, intense columns, the magnetic field allows the system to bypass the usual rules. The object can appear to exceed the Eddington limit for its total surface area because the energy is being released from two tiny, furious hotspots where the local physics are pushed to an extreme. The X-ray luminosity from these polar furnaces can be millions of times greater than the total output of our Sun. In their host galaxies, these pulsating ULXs are not just bright X-ray sources. They are often the single brightest persistent source of high-energy light, outshining the diffuse X-ray glow from all the other binary systems, supernova remnants, and hot gas in the entire galactic system. They are natural laboratories for conditions we cannot replicate, showing us how matter behaves when crushed by gravity and shaped by magnetism of a scale we can barely comprehend. Each steady pulse is a heartbeat from an object that defies a fundamental law, proving that in the cosmos, limits are not walls, but invitations for nature to show us a more ingenious design. A neutron star's defiance of the Eddington limit reveals the power of magnetic confinement. But what if that defiance goes one step further, into a realm of pure theoretical speculation? The universe's most violent transformations might not end with the supernova's final flash. There exists a hypothetical second act, a deeper collapse so profound it would rewrite the final chapter of a star's life. This is the theoretical Quark Nova, a concept that pushes the very boundaries of matter itself. Imagine the aftermath of a core collapse supernova. A neutron star is born, a city-sized object so dense that protons and electrons have been crushed together into a sea of neutrons. For decades, this was considered the ultimate state of matter before a black hole, but physics asks a deeper question: what happens inside that neutron star? Under pressures 100 trillion times greater than Earth's atmosphere, could the neutrons themselves break down? The Quark Nova hypothesis dares to say yes. In this scenario, the newborn neutron star is not stable. Over minutes, hours, or perhaps days, the unimaginable pressure at its core initiates a phase transition more fundamental than any other. The boundaries of individual neutrons dissolve, and their constituent particles, quarks, are set free. The entire star collapses inward once more, transitioning into a uniform soup of deconfined quarks, a state of matter that may have last existed a microsecond after the Big Bang. This sudden, catastrophic rearrangement releases a titanic burst of energy, triggering a second explosion from the heart of the already devastated stellar remnant. The light from this event would be unlike anything we have catalogued. It would be incredibly fast and brilliant, a sharp, superluminous spike that could potentially outshine even the brightest gamma-ray burst afterglow for a fleeting moment. Its spectrum would carry the unique fingerprint of this quark matter formation, a signature astrophysicists could hunt for in the aftermath of unusual supernova. The very possibility challenges our foundational understanding of nuclear physics and the equation of state for ultradense matter. It asks whether our current models of neutron stars are complete, or if they are merely waypoints on a path to something even stranger. While no event has ever been definitively identified as a quark nova, its theoretical shadow looms over certain anomalous observations. Supernova with inexplicably bright, brief secondary peaks in their light curves, or remnants that seem too energetic for a standard collapse, invite the question. What if a supernova is merely the opening act, and the true stellar death occurs when the remnant itself undergoes a metamorphosis into a new, alien form of matter? This speculative phenomenon serves as a powerful reminder. Our maps of cosmic catastrophe are still being drawn. The universe may reserve its most brilliant and transformative flashes not for the death of a star, but for the death of a star's corpse, revealing in that final, theoretical instant the fundamental building blocks of reality laid bare. That staggering concentration of energy is the true secret behind every phenomenon we have explored. The Milky Way's 100 billion stars collectively produce a gentle, steady light, a glow that has persisted for billions of years. Yet, for a fleeting moment, a single point can match or eclipse that entire integrated output. This is the profound difference between total energy and peak power, between a civilization's history and the flash of a nuclear bomb. These events are cosmic overclocking, where nature pushes its own systems into a brief, brilliant overload, focusing the equivalent of a galaxy's lifetime of starlight into a month, a week, or a single, blinding second. This extreme concentration is why automated sky surveys are our eyes on this volatile universe. Telescopes like Pan-STARRS and the upcoming Vera-C, Rubin observatories scan the heavens night after night, not to admire the static sky, but to catch it in the act of change. Their algorithms are trained to spot the new pinprick of light that wasn't there yesterday, instantly calculating its brightness and color. Is it a common variable star in our own galaxy, a routine supernova in a distant one, or something entirely unprecedented? The sheer intensity of the flash, measured against the known distance to its host galaxy, is the first clue. A light that momentarily rivals its entire galactic home is immediately flagged for urgent, multi-wavelength follow-up. This is how we separate the extraordinary from the mundane. It is how a brilliant flash of radio waves becomes a fast radio burst and not satellite interference. It is how the slow fade of a superluminous supernova is distinguished from the flare of a passing asteroid. Beyond their breathtaking spectacle, these events are not cosmic frivolities. They are essential, irreplaceable tools. Each one is a natural experiment conducted at an energy scale and under physical conditions we could never hope to replicate in any laboratory on Earth. The magnetic fields around a magnetar, the plasma physics within a relativistic jet, the behavior of matter at nuclear density, these are the frontiers of human knowledge, and the universe provides the experiments. By analyzing their light, we map the distribution of matter across cosmic time. We measure the expansion rate of the universe itself. We take an inventory of the cosmos's energetic budget, understanding how much power is locked in gravity, released in fusion, or transformed in annihilation. These rare, brilliant flashes are the universe's way of communicating its most fundamental rules, written in a language of extreme light. They remind us that to understand the calm, steady heavens, we must first learn to read its violent, luminous punctuation. This voyage through cosmic extremes is a testament to nature's capacity for both creation and destruction on a scale that defies human intuition. From the violent spaghettification of a star by a black hole's tied to the speculative, ultimate collapse into a soup of fundamental quarks, each phenomenon is a masterclass in the laws of physics written in light. These are not random acts of violence. Every brilliant flash, every enduring flare, and every cataclysmic explosion serves a profound purpose in the cosmic narrative. They are the universe's own laboratory experiments, conducted at energies and densities we could never hope to recreate, testing the very fabric of reality under the most extreme conditions imaginable. Through them, we witness the entire life cycle of cosmic entities, From the explosive birth of black holes and neutron stars to the violent deaths that forge the elements essential for planets and life itself. These events outshine their entire galactic homes not as a mere spectacle, but as a necessary consequence of their staggering power. That concentrated brilliance is their language, a signal beamed across the void. For eons, these messages traveled unseen, cosmic telegrams waiting for a recipient. Today, with our automated sky surveys and networks of telescopes, we are finally learning to decode them. Each flash we capture adds a new line to our understanding of gravity, magnetism, and the behavior of matter itself. They remind us with humbling clarity of our place in a dynamic and often unforgiving universe, a universe where tranquility is the exception and transformation is the constant. The story is far from over. As our technology advances with ever more sensitive instruments scanning the skies, we will undoubtedly discover new classes of these extraordinary beacons, phenomena that will challenge our theories and expand our imagination even further. The cosmos has only begun to share its secrets. If this journey through the universe's most brilliant and violent displays has sparked your curiosity, we would love to hear from you. Which of these rare cosmic phenomena did you find the most fascinating? Share your thoughts in the comments below. To continue exploring the greatest mysteries of space and time with us, please subscribe.